Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So in connection with the online lectures for the course of Fundamentals of Organic Chemistry, today we shall discuss about the Markovnikov Rule and Anti-Markovnikov Rule. So the basic concepts which we shall discuss in this lecture is we shall discuss about the alkenes, we shall discuss about general mechanism for addition reactions of alkenes, then we shall study about what is Markovnikov rule and the anti-Markovnikov rule. So alkenes, as you have studied earlier, these are unsaturated hydrocarbons that contain carbon-carbon double bond, right? So why we are saying that they are unsaturated hydrocarbon are the compounds that have carbon and hydrogen as part of the skeleton, right? So if you have any organic compound that has only carbon and hydrogen as part of their structure, then we say these compounds are hydrocarbons. And in case if a molecule has one or more than one double or triple bond, right? So if there is one or more than one double or triple bond, then in such cases we say that hydrocarbon is unsaturated. While in case if a hydrocarbon has all the bonds as single bond, right? If all the bonds between carbon and carbon are single, then in that case we say this hydrocarbon is saturated one, right? So alkenes are the unsaturated hydrocarbons that contain carbon-carbon double bond. General formula for alkenes is CnH2n, right? And the simplest member of alkene is ethene with the formula of C2H4. So it is a carbon-carbon double bond between those two carbons, and we also know that the alkenes are known as olefins. So olefins mean oil forming, right? So why they are called olefins? Because the lower member of alkenes, such as the ethene, propene, or ethylene or propylene, etc., so these reacts with halogen to form oily products. That's why the lower member of alkenes are known as olefins, right? So it's important to note that not all alkenes are called olefins. Only the lower member of alkenes are known as olefins, and they are called olefins because once they react with halogens, they form oils, right? So in today's lecture, we shall study about how we carry out addition of different reagents on a carbon-carbon double bond. But before going to the addition reactions, let's consider the term which is known as symmetrical and unsymmetrical alkene, right? So when we say that alkene is symmetrical or something else is symmetrical, it means that if we break or if we cut that molecule into two halves, the two halves are exactly the same, right? So for example, we have an alkene and we have to cut this molecule like that, right? So if I cut this molecule into two, then these two halves, right? So you can see this half and this half, right? So if these two halves are exactly same, then we say that alkene is symmetrical. But in case if the two halves are different, we say alkene is unsymmetrical, right? So in this specific case, you can see that when we have broken the bond from here, so the two halves are different, they are not the same. We say alkene is unsymmetrical, right? Here another example, suppose we cut this alkene into two halves. Again we say that this half and this half and this half, both halves are exactly same, right? Why we are saying the same? Because this carbon has a hydrogen and a methyl. Similarly, this carbon also has a hydrogen and a methyl group. So both the fragments of this carbon-carbon double bond are same, right? So don't just get confused about cis and trans configurations. So just see that in both the fragments, this carbon has a hydrogen and a methyl. Similarly, this carbon has a hydrogen and a methyl. So those fragments are same. This alkene is symmetrical. Now we have another example. Let's consider, so we cleave this alkene. So when we break this alkene into two halves, so we can say that this half has carbon with a methyl and hydrogen, while this carbon has two methyl groups. So both halves are different. So this alkene is unsymmetrical. Now we have an alkene like that one. So if we cleave them, so both halves are the same. So since both halves are same, the alkene is symmetrical. Similarly, we have another alkene. So here you can say the carbon has 2 methyl and this carbon also has 2 methyl groups, right? So this alkene is also symmetrical. Alright, so you must know about the terms of symmetrical and unsymmetrical, right? So in this specific case, we are just considering about the symmetrical alkene, unsymmetrical alkene. Similarly, we shall see about symmetrical reagents or unsymmetrical reagents. But this concept of symmetry is the same in organic chemistry, whether there's alkene or any other reagent or any other functional group. So whenever you see the term of symmetrical, just keep in mind that it means that if you cut a molecule into 2 halves, so if both of the halves are same, then molecule will be symmetrical, but if the 2 halves are different, then molecule will be unsymmetrical. So here we have some unsymmetrical reagents and symmetrical reagents, right? The concept of symmetrical reagent and unsymmetrical reagent is just like the concept of symmetrical alkene and unsymmetrical alkene, right? So if you have to check whether the reagent is symmetrical or unsymmetrical, just break the reagent or cleave the reagent from the center. So if after cleaving you get the 2 halves that are same, then reagent will be symmetrical. But if you cleave the bond and the 2 halves are different, right? For example, if I cleave this bond from here, then both of the halves are different because on one side we have a chlorine and on the other side we have a hydrogen. Similarly, so here we have a chlorine and here we have an iodine. Although both are halogens, but they are different halogens, right? So this reagent is also unsymmetrical. Here we have chlorine and chlorine. So if we cut the molecule, if we cut this reagent into half, both halves will be same. So this reagent is symmetrical reagent. So if I cleave this from the center, so here I have a hydrogen and a hydroxyl. So both of the reagents are, both of the parts are different, so this reagent will be unsymmetrical. Similarly, this is also unsymmetrical because both the halves are different. Similarly, this is an unsymmetrical reagent because on one side we have a hydrogen, on the other side we have sulfonic group. Similarly, this is also an unsymmetrical reagent, right? So in this lecture, it's important for you to know what is symmetrical reagent or unsymmetrical reagent, what's a symmetrical alkene and an unsymmetrical alkene, right? So since we are considering the addition reactions to alkenes, let's consider the general mechanism of addition of alkenes, right? So as you have already studied that alkenes normally undergo addition reactions, right? So why addition reactions? Because the alkenes are unsaturated. They want to get converted into saturated compound, right? So just remember that all saturated compounds have all of the bond as single bonds, right? So alkenes want to become saturated because they have a double bond here, right? So for that reason, the alkenes undergo addition reaction, right? And in these reactions, we get a carbocation as an intermediate. So just general mechanism for this reaction. So we have a pi bond here. So as you have studied in the previous lectures, this pi bond is electronically rich, right? So this pi bond will act as a nucleophile or Lewis base. So this bond, pi bond, will attack on this deficient electrophile, right? This part which is partially positive, this is deficient. So anything that's electronically deficient, we have studied that this is known as an electrophile, while this component will leave as a nucleophile here. So in the start of this mechanism, the pi bond will attack on this electrophile which is electronically deficient, and this nucleophilic component will leave. So as an intermediate, we will get a carbocation here, right? After formation of this carbocation, this component that was a nucleophile which was left in the previous step, this nucleophile will attack as a nucleophile here, and we will get a saturated compound here, right? So this is the general mechanism of addition of alkenes. So in order to just understand for our simplicity, we divide the addition reactions of alkenes into 4 groups, right? So the group 1 is addition of symmetrical reagent to symmetrical alkene. The second group is addition of symmetrical reagent to unsymmetrical alkene. Third group is addition of unsymmetrical reagent to symmetrical alkene, and the fourth is the addition of unsymmetrical reagent to unsymmetrical alkene, right? So these are the four categories of addition reactions to alkenes, and we shall study them one by one. So firstly, we have the addition reactions of symmetrical alkene to addition of symmetrical reagent to symmetrical alkene, right? So here we are taking the example of this alkene, which is symmetrical. So you can check if I draw a line here, if I leave it from here, so the two halves are exactly same. So this alkene is symmetrical. Similarly, if I cut this reagent into half from here, so both the halves are exactly the same, right? It means that our reagent is also symmetrical and our alkene is also symmetrical, right? So let's just consider that we are carrying out the addition reaction. So we are mentioning the carbons in different color in order to differentiate them, right? So let's consider that the reaction involves the attack of pi electrons on one of the hydrogens, because by means of London dispersion forces, so one of the hydrogens is partially positive while the other hydrogen is partially negative, right? So pi electronic density attacks the deficient hydrogen at that instant, and the other hydrogen will leave, like that. So there are two possibilities, right? This hydrogen can attach to this carbon, which is green, or this hydrogen can attach to the carbon, which is blue, right? So since both of the carbon has same hydrogens, right? So this hydrogen can add to this blue carbon, or this hydrogen can attach to this green carbon, right? So if you see that in both of the cases, whether the hydrogen is getting attached to this green carbon or blue carbon, we are getting a carbocation which is primary, right? So here this carbocation is primary carbocation, and similarly this carbocation is also a primary carbocation. So whether the hydrogen adds to this carbon or that carbon, it doesn't matters, right? So we get same carbocation here, right? And afterwards what happens, that this hydrogen that left in the previous step, so this hydrogen will attack as a nucleophile on the carbocation right here, or in that case this hydrogen with negative charge will attack on this carbocation here, and we will get only one product, right? So we can make a generalization that when both the alkenes and the reagents are symmetrical, it doesn't matter that which of the two hydrogen atoms will go to which carbon, right? So this hydrogen can go to this carbon or that carbon. Similarly, this hydrogen can go to this carbon or that carbon, right? So whenever the reagent and alkene both are symmetrical, it doesn't matter that which atom goes to which carbon. So we get only one type of carbocation and we only get one product, right? So here is a generalization. So we'll consider this generalization on another system. So let's consider that now we have an alkene and a reagent, and we'll see that whether this is symmetrical or unsymmetrical, right? So just check. So in order to check, so we break this alkene into two halves. So both the halves are exactly same because both carbon has two hydrogens here. So we know that alkene is symmetrical. Now we leave this reagent into half, so both our halves are same, so it means the reagent is also symmetrical, right? So this is a case of addition of symmetrical reagent to symmetrical alkene, right? So as per the mechanism, we know that because of London dispersion, so one of the carbon is partially positive at this instant, other is partially negative. So this pi electronic density will attack on this deficient chlorine, and the other chlorine will leave, like that, right? So we have two possibilities. This chlorine can attach with this green carbon, or this chlorine can attach with this blue carbon. So let's consider both options. So here in this case, the chlorine is getting attached to the blue carbon here, and in this case this chlorine has attached to the green carbon here. So what you have to check is to check the nature of carbocation, whether the carbocations are different or they are the same. So in this case the carbocation is primary, and in this case the carbocation is also primary, right? So we are getting the same carbocation here. So in the next step, the chloride ion that left in the previous step, this chloride ion will attack as a nucleophile here, and similarly this chloride will also attack as a nucleophile here. So since the carbocation is the same, the product formed after this attack of chlorine will also be the same, right? So again, we can generalize that since both the reagent and the alkene are symmetrical, it doesn't matter which of the two halogen atom will go to each carbon, right? This chlorine can go to this carbon or that carbon. It doesn't matter because we only get one carbocation, and this one carbocation will form only one product, right? So this is a generalization in case we have we have symmetrical alkene and symmetrical reagent. Now we have the second category, addition of unsymmetrical reagent to a symmetrical alkene, right? So in this specific case, we have an alkene which is symmetrical, right? So you see alkene is symmetrical, but the reagent is unsymmetrical. Right, you can see the both halves are different. So on one side we have a chlorine and the other side we have a hydrogen. So in this specific case, since the alkene is symmetrical and the reagent is unsymmetrical, let's consider what will be the outcome of this addition reaction. So as you know, as per the mechanism, the pi electronic density will attack on the carbon, will attack on the part of reagent that is electronically deficient. So here we have an electrophilic part, while this nucleophilic part will leave for now, right? So we have two options. This hydrogen can go to this green carbon, or that can go to that blue carbon, and we will see what type of carbocation we get. So suppose this hydrogen is getting attached to this blue carbon. In that case, we are getting a carbocation, and you can see this carbocation is primary. While if the hydrogen goes to the green carbon here, then again we are getting a carbocation here, and you can see this carbocation is also primary, right? So although the reagent is, we can say this is unsymmetrical, but when this first part with this is a formation of carbocation here, so whenever the alkene is symmetrical while the reagent is unsymmetrical, we get only one carbocation here, right? So we get only same type of carbocation. The next step will be this chloride ion that left in the previous step. So this chloride ion will attack as a nucleophile on this carbocation. Similarly, this chloride will also attack on this carbocation, right? And we'll get the product. So you can see the both of the products are same, whether you write it this way or you write it that way, right? It doesn't matter because this chlorine which is attached to carbon, this carbon is further attached to two hydrogens. Similarly, in this case, the chlorine which is attached to carbon, this carbon is further attached to two carbons. So it doesn't matter about the product. Both of the products are same. So in case of addition of unsymmetrical reagent to a symmetrical alkene, we can make a generalization that although the reagent is unsymmetrical, but since the alkene is symmetrical, it doesn't matter which of the two atoms, hydrogen or chlorine, will bond to which carbon, right? Only one product will be obtained. So since we are getting only one carbocation, therefore the product will be the same in both cases, right? So this is the case of addition of unsymmetrical reagent to a symmetrical alkene. So let's consider another example. So here we have again an unsymmetrical reagent and a symmetrical alkene. You can see, so if we break the bond between carbon and carbon here, so both of the fragments are exactly same, right? So this alkene is symmetrical, but if I break this bond from center, so here we have a hydroxyl and a hydrogen, so both of these parts are different, right? So this is a case of unsymmetrical reagent and symmetrical alkene, right? So as per the mechanism, the electronic density will attack on this hydrogen here. So the hydrogen can go to that carbon or that carbon, so it will not make any difference because we will get only one type of carbocation, right? So you can just draw the carbocation which will be formed when hydrogen gets attached to this green carbon or when hydrogen gets attached to this blue carbon here. So since we get only one type of carbocation, so we will get only one type of product as well. Right, so whether you write it this way or you write it that way, it doesn't matter, because in both of the cases this hydroxyl is attached to carbon, which is further bonded with two hydrogens. Similarly, this hydroxyl is attached to carbon, which is further bonded with two hydrogens here, right? So as a part of generalization, we can say that whenever there is addition of unsymmetrical reagent to a symmetrical alkene, then it doesn't matter which atom goes to which carbon. Right, we get only one type of carbocation and we get only one type of product. Now we have third type of addition reaction to alkene. In this case, we have symmetrical reagent, and this symmetrical reagent is adding to an unsymmetrical alkene. Right, so here we have an alkene. Just cleave the bond from center. You can see both the halves are different. So here we have a carbon with two hydrogens, and here we have a carbon with two methyl groups. So both the halves are different, so that's why we say the alkene is unsymmetrical, while this hydrogen is symmetrical. Right, so you can see about the mechanism. So let's draw the mechanism here. So because of London dispersion, suppose this hydrogen is partial positive at this instant and this hydrogen is partial negative, right? So in the reaction, this bielectronic density will act as an electrophile, nucleophile on this hydrogen, and the other hydrogen will link with them, right? So now we have possibility that this hydrogen gets attached to this green carbon or that blue carbon here. So we will see both possibilities, and we'll check whether we get same carbocation or different carbocation. So let's consider this hydrogen gets attached to blue carbon here. So if hydrogen gets attached to this blue carbon, so we'll get a carbocation here. So you can check this carbocation is a tertiary carbocation. Why tertiary? Because this positively charged carbon is further attached with three carbons here. Right, this carbon is tertiary carbocation here, and this carbocation, this is a primary carbocation here, because this positively charged carbon is further attached with only one carbon. Now we are getting two different type of carbocations here. Just remember that tertiary carbocation is more stable as compared to primary carbocation. Furthermore, also keep in mind that if carbocation is more stable, it is also formed to more extent. So this tertiary carbocation, this is more stable, that's why it will be formed to more extent, while this carbocation will be formed less because it's unstable. So in the next step, this hydride ion that left in the previous step will act as a nucleophile, and it will attack on this carbon or it will attack on this carbon, both possibilities, right? So if this hydride is attacking on this carbon, right, sorry, this is a hydrogen here, so that's a mistake, you can just correct it here. So this is a hydrogen here and similarly a hydrogen here, right? This hydride, if it attacks on this carbon, so we get a product like this one, and if it attacks on this one, so the product will be this one. So this is a some different case. So in case when you are adding a symmetrical reagent to an unsymmetrical alkene, although we are forming two different type of carbocations, one is stable, one is less stable, but the product that is formed from both of these carbocations is the same, right? Although we are getting two different carbocations, one is tertiary, one is primary, but by the end we get the same product, whether the reaction is with primary carbocation or a secondary carbocation. So here we can make a generalization that since the alkene is unsymmetrical, we get two different carbocations, but since the reagent is symmetrical, the attack of the nucleophile, right, that's the nucleophile, the attack of the nucleophile results in formation of a single product. And it doesn't matter which part goes to which carbon again, right? So in all of the previous three cases which we have studied so far, we get only one product, whether the carbocation is formed is same or whether the carbocation formed are different. So now we are considering the fourth category of this reaction. Okay, another example of this condition, when we are having a symmetrical reagent which is added to an unsymmetrical alkene, right here. So we have chlorine, you can see this is a symmetrical reagent while this alkene is unsymmetrical. So again we are having two different type of carbocations. So one carbocation is tertiary, this is more stable. This carbocation is primary, this is less stable, but after the attack of chlorine, which is nucleophile here, so we get the same product, right? So we can make a generalization that since alkene is unsymmetrical, we get two different carbocations, but since the reagent is symmetrical, the attack of nucleophile result in formation of only one product. So here we have the fourth category of addition reaction to alkenes. The fourth category is we are adding an unsymmetrical reagent to an unsymmetrical alkene. So just see the mechanism for this purpose. So here we have a mechanism. So you can say pi electrons will attack on this partially positive center, right, and this group will leave as a nucleophile. Again we have two possibilities, right? So this hydrogen can attach to this green carbon or this blue carbon. So as a result you can see that alkene is unsymmetrical, so you'll get two different types of carbocations. So one will be more stable and another will be less stable, right? So suppose that in case if we are having a green carbon here, right, and this is bonded and this is a blue carbon here, right, and we are having a methyl group here, a methyl group here, a hydrogen here, and another hydrogen here as well, right? So let's consider the possibility that the hydrogen gets attached to this blue carbon here. So if hydrogen gets attached to this blue carbon, we can say we are forming a carbocation here. So this carbocation which will be formed, this carbocation is tertiary. But in case if this hydrogen, if it gets attached to this green carbon, right, so just let me draw it. So if this hydrogen, if it gets attached to this green carbon here, then we get a carbocation on the blue carbon. So this carbocation which is on this blue carbon, this carbocation is primary. So this carbocation is primary carbocation. We're getting two different types of carbocation. So one is tertiary and one is primary. So you know the tertiary carbocation is more stable, that will be formed more extent, while this primary carbocation will be formed less because it's less stable. So in the next step what happens that this chlorine atom that left in the previous step, this chlorine will attack as a nucleophile on this carbocation here. So in that case, if the chlorine is attacking here, we get this product, right? So this product is forming from a more stable carbocation, while the chlorine, when it attacks on this carbocation, so this carbocation will result in formation of this product. So this product is forming from a carbocation that is less stable. Now let's consider if these two products are same or if these two products are different. So first consider this product. So here you can see that the chlorine is attached to carbon, which is further attached to two hydrogens, while in this example, in this product, this chlorine which is attached to carbon, which is attached to two hydrogens, two further methyl groups here, right? So both of these groups are different. You can see for example here. So since both of these groups are different, so these products are different, right? So we can make a generalization from this explanation is that whenever an unsymmetrical reagent is added to an unsymmetrical alkene, we get two different type of carbocations, and these two type of carbocations result in formation of two different products after the attack of the nucleophile, right? So we get two different type of products. Now here the question arises, which of these two products will be major, right? So what's a major product? Major product is a product that is formed in a more quantity, in more yield, right? So we get two different products, right? They are not same, they are different, because you can see this chlorine is attached to carbon, which is attached to two hydrogens, while this chlorine is attached to carbon, which is attached with two methyl groups. So we are getting two different groups, two different products. And now the question arises, which of these two will be major? Which of these two will be formed in larger quantity? For this explanation, let's consider the mechanism here. You can see this bielectronic density is attack on this electrophilic part, whatever the electrophilic part is, right? So just keep in mind that this reagent is unsymmetrical and this alkene is also unsymmetrical here, right? So when it attacks this electrophilic part, so we are getting two possibilities. So this electrophile can attach on this green carbon or this blue carbon. So depending on the carbon to which this electrophile gets attached, we get two different types of carbocation here. So in case this electrophile is getting attached to this green carbon, then we get a primary carbocation here, right? So primary carbocation is less stable, while if the electrophile is attacking on this blue carbon, we are getting a tertiary carbocation here. So since tertiary carbocation is more stable, it is formed in larger amount, that is formed as a major carbocation, and the product that's formed from this major carbocation will also be formed in larger amount. This carbocation, since it's forming in lesser quantity, therefore after attack of the nucleophile, the product will also be formed in lesser quantity, right? So we can make a generalization here that a carbocation that is more stable will result in formation of a major product, while the carbocation that's less stable will result in formation of a minor product, right? So why we say that certain products formed as major while others formed as minor? Answer is relative stability of carbocation here. So if the carbocation is more stable, it will be formed in more amount, and the product formed will also be in higher yield, right? The product that's formed in higher yield or in more amount is called a major product, right? So in general, we can say stable carbocation will form the major product, while unstable carbocation will form the minor product. So here is an important rule, and the rule was devised by Russian scientist Markovnikov. The rule is named after Markovnikov. According to this rule, whenever an unsymmetrical reagent is added to an unsymmetrical alkene, the positive part of the added reagent will always go to the carbon that has maximum number of hydrogen atoms, right? So here the positive part of the added reagent means the electrophilic part, right? So it is important for Markovnikov rule to be followed that both the alkene and the reagent must be unsymmetrical, right? If any of the reagent or the alkene or both are symmetrical, Markovnikov rule cannot be followed. It is only followed if the alkene as well as the reagent are unsymmetrical, right? So whenever both of these are unsymmetrical, then the electrophilic part, which is the positive part, will always go to the carbon that has maximum number of hydrogen atoms, right? Let's apply Markovnikov rule on an alkene, right? So first part of the Markovnikov rule is whenever an unsymmetrical reagent is added to an unsymmetrical alkene. So alkene is unsymmetrical, reagent is unsymmetrical. The positive part of the added reagent will go to the carbon that has maximum number of hydrogen atoms, right? This is the positive part of the added reagent. This is electrophilic part. So according to this rule, this positive part should go to the carbon that has maximum number of hydrogen atoms, right? So you must check the carbon which is doubly bonded. This carbon must be having higher number of hydrogen atoms. Don't count the hydrogen to this methyl group, right? So these hydrogens are not directly bonded to the doubly bonded carbon. You must check for the carbon which is doubly bonded and to this how many hydrogens are attached, right? So according to this rule, this hydrogen must go to this carbon because it is having maximum number of hydrogen atoms. This carbon has no hydrogen, while this carbon has 2 hydrogen atoms. So why this rule is saying that this positive part must go to the carbon that has maximum number of hydrogen atoms, because if hydrogen goes to this carbon, then we get a carbocation which is stable. If the hydrogen went to this carbon, then we would have got a carbocation that is less stable, right? So this is the Markovnikov rule that whenever both of alkene and reagent are unsymmetrical, then the positive part of this reagent should go to the carbon that has maximum number of hydrogen atoms, right? Why? Because in this way we'll get a more stable carbocation, and this more stable carbocation will result in formation of a major product, right? Now we have another rule which is known as Anti-Markovnikov rule. It was devised by another scientist named Morris, right? This rule is also known as Harash rule, and it's also known as peroxide effect, right? Both are the names for the same rule. So according to this rule, whenever an unsymmetrical reagent is added to an unsymmetrical alkene in the presence of peroxide, right? It's important for you to note here that this is an additional thing, in the presence of peroxide, then the positive part of the added reagent, which means electrophile, will always go to the carbon that has minimum number of hydrogen atoms, right? You can see this Markovnikov rule and Anti-Markovnikov rule are exactly opposite of each other, right? The statements are almost the same, except that in the statement of Anti-Markovnikov rule we have added the statement in the presence of a peroxide, right? So you must have an reagent which is unsymmetrical, you must have an alkene which is unsymmetrical, and the reaction must take place in the presence of a peroxide. Under these conditions, the positive part of the reagent will go to the carbon that has minimum number of hydrogen atoms, right? So why we are saying that the hydrogen must go, or the positive part must go to the carbon that has minimum number of hydrogen atoms, this can be explained from this mechanism here. So here we have a peroxide. This is hydrogen peroxide, right? So what's peroxide? Peroxide is any group that has carbon, that has a single bond between oxygen and oxygen, right? So here we have a single bond between oxygen and oxygen, right? So any functional group that has a single bond between oxygen and oxygen, this is known as peroxide. So this is a hydrogen peroxide molecule. So this hydrogen peroxide, what is speciality, that whenever you expose it to light or whenever you expose it to heat, this bond undergoes homolytic cleavage, right? So you remember that whenever there is a homolytic cleavage we get free radical. So as a result of this homolytic cleavage we get two hydroxy free radicals. You can see here we are having an unpaired electron here, so this is a free radical here, right? So whenever reaction takes place in the presence of peroxide, what happens that this peroxide undergoes homolytic cleavage and it forms this free radical. Now this free radical reacts with the reagent first, right? So in normal mechanism what is happening that the double bond was attacking on the reagent, but in case when you are using a peroxide, it is the peroxide or it's the free radical that is firstly reacting with the reagent here, right? So what happens, this hydroxy radical will react with this HBr and result in formation of a water molecule and a bromide radical. So we are getting a Br free radical, right? So this Br free radical will firstly react with the alkene, right? So in the previous case, in the case of Markovnikov, what was happening, the reagent was directly attacking with the alkene and the positive part was going on the carbon that was having maximum number of hydrogen atoms. But now this reagent is firstly reacting with the free radical and we are getting another free radical here. So this bromide radical will attack on the alkene. So Br is a bulky group, right, that has a larger size. So this larger group will prefer to go to a carbon that has minimum number of substituents, right? So Br will prefer to go to a carbon that has minimum number of substituents because the minimum number of substituents will provide minimum steric hindrance. So this bromine will prefer to go on this carbon, right? So when this bromine will prefer to go on this carbon, right, so pi electrons of the bromine and the pi electrons of this carbon will pair up. So there will be single bond between carbon and bromine and we'll get a free radical on this carbon here, right? So if the bromine is going on this terminal carbon which is less substituted, which is less bulky, so we'll get a free radical here, right? So this free radical is a secondary free radical, right? The other possibility is here that instead the free radical is going on this carbon. Suppose that bromine goes to this carbon, right? It has the disadvantage because this methyl group will hinder this Br radical, right? So bromine doesn't want to go here, but suppose bromine goes on this carbon. In that case, then we will get a free radical on this carbon, right? Like this. This free radical is a primary free radical, right? So here we have a secondary free radical and here we have a primary free radical, right? So just like the carbocation, the secondary free radical are more stable than primary free radical. So this is more stable. Since this is more stable, it is formed in more amount. Therefore, the product that will be formed from this product will be formed in more amount. So if you see overall the product, you can see that according to Anti-Markovnikov rule, when an unsymmetrical reagent is added to an unsymmetrical alkene, then the positive part of the added reagent will go to the carbon that has minimum number of hydrogen atoms, right? So in this example, this carbon has 1 hydrogen while this carbon has 2 hydrogens. This is minimum number of hydrogen atoms, so positive part should go to this carbon while the other part should go to that carbon. The reason why, because that is Anti-Markovnikov rule is related to this relative stability of free radical. Markovnikov rule is related to the relative stability of carbocation here, right? So this is the difference in mechanism here. So just remember that whenever you are considering a reaction in the presence of peroxide, then Anti-Markovnikov rule is followed. And whenever you are carrying out a reaction in the absence of peroxide, Markovnikov rule is followed. Further, also remember that Markovnikov rule or Anti-Markovnikov rule can only be followed in case if the reagent or the alkene is unsymmetrical. So if any of these becomes symmetrical, Markovnikov rule or Anti-Markovnikov rule cannot be followed, right? So that's all for this lecture. I hope you have understood it well. Thank you for your patience.